what are the basics questions that are from the previous exams. Okay, so today the main focus is uh, what are the previous questions that we are getting from the previous gate papers from the chapters of two chapters like sex relations like that. Okay, so that is our main focus today. So we'll start discussing that. So let us, I have some 20 questions are there. Among the 20, whatever possible questions, we'll try to solve those. Okay, one second, I will. Okay, is PPT is visible? Okay. So today we will discuss few questions from the two concepts. There is a mathematical logic, sets, functions, and relations from the previous papers. Okay. Is it audible or okay, all of you?
Yes, sir.
Yes, Mahesh. Thank you. Thank you. So let us see there. We have a question like this. Consider the following expressions. Uh, he given the five expressions like false, Q, followed by true, PRQ, negation QRP. So these are the five expressions or well-formed formulas that are given. And he is asking the number of expressions given above that are logically implied P and P implies Q. Okay. So that what is here we have this particular five expressions are there. So among these five expressions, so the number of expressions which are given above that are logically implied by this P and P implies Q. Okay, so that is the question given. So now try it first in whatever the case, just try to understand the question what is given. Okay, so that we can answer that in the easy way. Okay, so let us, what the meaning of this is, in which of the above statements are logically implied by P and P implies Q. That means, so let us, if you assume these are X, whatever it may be X, logically implied, here given that logically implied, that means X logically implies like this, P and P implies Q. Okay, that is actually the statement given. So this X may be either false or Q or true or PRQ or negation PRQ. So when we can say that this is logically implied. So if we construct the truth table for this, or just if you are getting it is a tautology, if it is approved as a tautology, so then I can say that so these expressions can logically imply this P and P implies Q. Okay, so just we'll try to, so indirectly what is the meaning that, so by considering this one as any of that in the place of X, what we have to do is we need to construct the truth table. So tautology means what we need to get, that is we need to get all the cases as true. Okay, so let us we'll do it fast. As here, if you observe all the expressions, we have only two cases are there. That is two variables are there. So true, 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 false, false, true, and coming to false, false. Now, first I'll try to do this for one. P implies Q here I have. So P implies Q means true, false, true, true, and P and P implies Q. Okay, this is a given here. So P and P implies Q means, so this one and this one. So true, this is false, this is also false, and this is also false. Now I got this one. Now in the place of X, that means false. Let us see here. False tautologically implies, let us, this is A. Okay, now we'll check here. So for this, false implies this A means we'll consider all the cases as false here. Okay, so this is false here, and false implies A. So now what you have to do? So this is the false one, and this is another one A. So false true will get true, false false will get true, false false will get true, false false will get true. So here we got this true. That means this false can tautologically implies this particular total expression. Similarly, if I consider Q here, in the place of Q, here we have already Q and this P and P implies Q. So between this one and this one we need to find out whether we need to get tautology or not. See here, true true will get true, false false will get false, true false it is false. Okay, sorry, true implies true true, false implies false, that is also true, and true implies false will get false. So that, so this here Q will not get here. So false will get here, Q will not get here. Like that you have to do for all the cases. Okay. So if you check all the cases like this, so this one, this P and P implies Q will logically implied from this false and true PRQ negation QRP. Okay, from these four expressions, we can derive this one. What is the meaning that false implies P and P implies Q? That is true. Similarly, true implies P and P implies Q. So if you construct truth table for this, it also to get true. Similarly, PRQ, okay, PRQ and this one will get true. Now, similarly, negation QRP for the last one, again if you get this one, for that also if you construct the truth table, get true. So that is the statement. So this is the numerical type of numerical value that we need to give it as answer. So 4 is the answer for this. So next, second one, let us here given that P, Q, R, S represents the following expressions. Okay, so P is representing X belongs to 8, 9, 10, 11, 12. Q is representing X is a composite number. R is X is a perfect square, and X is a prime number. Now here, these are the propositions given, and the statement here given is the integer x greater than or equal to 2. So that is x is greater than or equal to 2, which satisfies this given expression. So satisfies means what we need to get is this entire expression should result to true. Okay, that is the main thing we have to satisfiable. We have a concept called as satisfiable. When a formula is satisfiable is if it is deriving to true, so then we can call it as a satisfiable. So now let us see here. If directly solve this one, we may found little bit difficult. So that try to just what we are going to do there is we'll try to simplify this. Later on we'll apply this thing. Okay. So what we have to do is here we have that particular expression. So this expression should result to true. Okay. So if you are getting true, then what is the case that you have to consider here? So this 11 is the result. Let us see how we are going to process this one. Here he given that negation of P implies Q and negation R or negation S. Okay, so this is the statement given. Now this is negation of, here this P implies Q can be written as negation PRQ and negation R or negation S. So like that I can solve this one. So later on, so before applying this De Morgan law for this, first I will try to do this. So negation of P or Q, this will be written as this, and this can be written as negation of R. This R becomes and yes. Okay. Now I will apply De Morgan. This has one expression. This has another expression. So negation of negation P or Q. So this and becomes R now, and this is negation R and S. Okay. So now here, if you apply this one, what happens is P, it will becomes P. This R becomes an negation Q R. So here it is double negation, so that we will get it as R and S. So now here, this is a simplified expression for this. Now see here, what we are expecting here from this statement. Okay. So this entire expression, as we already told, should be true. Okay. If we want to make it as true, so see there, what is the connective that we have here is, that is R connective. That means R means true, 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 false, that is false, false, true, okay, and false, false. Okay, that means, so if you need, sorry, this is R now, okay. So if you are getting true, true, will get true. We are getting true, false, true, false, true, true, false, false, false. Okay, now true we need to get here, so that the first three cases we have to consider here. In the first three cases, so we are going to consider these particular values. Okay, so now here if you see here, as the final result that we are expecting is true means, so your first expression may be true, second may be true, first expression may be true, second may be false, first expression may be false means then second expression should be true. Okay, so now from this what we have to do is, now we can check out whether the statements which will follow this particular rule or not. Okay, let us, I will first try to R and S, I will try to solve this R and S, whether it will be become true or false like that. So R and S means we have like this: R is a perfect square, and sorry, X is a perfect square, X is a prime number. So that means R and S, we need to combine these two statements. So R and S means we need to find out the number which will satisfy this both the two. Okay, so perfect square should be there and prime number should be there. Okay, let us see here. If you see the prime number is 11. Okay, and it is not perfect square. Okay, so that what happened to this R and S here, it is not possible to get true, so we will get false only. Okay, so that if you are getting false here, what is the expecting value that from this side is P and negation Q should be true. That means this P and Q should be true. Okay, so now here that is P and negation Q. P is this numbers, what are that is X belongs to 8, 9, 10, 11 and 12. Okay, and negation Q, so this is P. Negation Q means it should not be a composite number. It should not be a composite number. So now here, other than prime numbers, all numbers are treated as a component number, composite number. That means if you have the, if the number is having factors, then it is going to be called as a, what we can say, that is so that is that numbers are called as a composite number. Now here, if you see, observe this particular example here. So this 11 is the number which will satisfy this particular rule. Okay, so that finally we got the 11 as the result. And coming to this R and S, it becomes false. That means it is not possible to get into that. So that 11 becomes the result that we need to derive. Or after simple like that, we can process this one, or after simplifying this one up to this, that is a P and negation Q, or R and S. Now just you apply the propositions whatever we have, and you can identify the number which will satisfy this particular property. So like that we can do this one. Okay, so regarding this is the second one that you can consider here. And see, we go with another one, third question. Let us see there. It is what we can say, that is a hypothetical question, like something like that. That means we need to think it in the large way. In a room there are, okay, in a room there are only two types of people. Okay, so namely type 1 and type 2. So we have room. Okay, in the room we have two types of people, type 1 and type 2. Type 1 people always tell truth. That means he will tell true, and type 2 people will always tell lie. So let us, it will become false. Okay, so now you give a fair coin to a person in that room. Okay, let us a coin is given to this in this particular room to any one of the person. We don't know who is that person, whether he belong to T1 or he is belonging to T2. Okay, so you give a fair coin to the person in that room without knowing which type of he is from, and tell him, so we don't know who is that person, but we given the coin, and tell him to toss it and hide the result from you. Okay, so we are giving that coin and asking to toss it, and whatever the result we are getting, that should be hide. Okay, so now hide from you till you ask for it. Upon asking, the person replies the following. Okay, so now the tossing process is completed and he got some result with him. Now we are asking that particular person, and that person is replying like this. So the result of the toss is head if and only if I am telling the truth. Okay, see, observe this statement, little bit confusing here. Okay, so here the result of the toss is head. if if and only if I am telling the truth. Okay, see here the connective we have here is if and only if. Okay, that means here we have going to consider here. So at one of the event is toss. Okay, if the result of the toss is head. Okay, so that is the result of the toss is head. Okay, so that is if R implies, let us H, okay, is head, then I am telling truth. Okay, then means let us T is telling T1 implies T2, like that. Now from this statement, now we have to check out which of the following options are correct. Okay, so we have to finalize that whether we got the result as a head or we got the result as tail, or if the person is of type 2, then the result is tail, that is tail. If the person is of type 1, so 2 is repeated here. If the person is of type 1, then the result is tail. Okay, let us see about the C statement and D statement. If the person is type 2, okay, so type 2 means he will always tell lie. Okay, so that coming to this option C, if the person is type 2, then the result is tail. That means here we got that head. Okay, so similarly, the person is type 1, then the result is tail. So that means type 1 person is telling truth always, so that here it is getting tail as a result. Now see there is a conflict, that here we are getting head or here we are getting tail, so that these two statements are not possible. Okay, and we can get that answer from the first one, that is the result is head for this one. Okay, so why? Because so here if type 1 person is telling truth means he will so let us see here, type 1 person is telling truth means the tile so this becomes true, but this is not true and this is also not true. Okay, so that we are getting this particular A as the answer for this one. So we need to think this particular statement logically, and then you have to process this one. And coming to the statement 4, it is a little bit easy process. Okay, here he given two statements. One of the statement is S1 and other one is S2. If a candidate is known to be corrupt, if a candidate is known to be corrupt, then he will not be elected. And S2 is given as if a candidate is kind, then he will be elected. So which one of the following statements follows from S1 and S2 as per the sound of inference rules of logic? That means from S1 and S2 we have to derive a result. Okay, so in terms of problems, this is the one of the hypothesis given and this is another hypothesis given. From these two statements we need to derive the conclusion. Okay, so first we'll try to represent these two statements in symbolic notation. Let us see here, if candidate is known to be corrupt. Okay, so now we are going to represent it as by means of if then. Okay, so that candidate is corrupt, let us see, it will be represented as C implies then he will not be corrupt elected. Okay, not means just I will give negation E. C implies negation E, like that. Okay, so if a candidate is known to be corrupt, that is C, then he will not be elected. So that here I am representing it as negation E. Next, second statement S2. If a candidate is kind, so let it be K, then he will be elected. That means here I am going to consider E. Okay. Now this is the statements we got. We represented in the symbolic notation. Now first what you have to do is we need to use these two statements and try to solve what is the conclusion we are getting here. Okay, now let us see here. If you see that directly, it is not possible to do the process here. First I can use this one, C implies negation E. Okay, I will introduce this one and after that I will only two there, K implies E. Okay, so we have a formula, P implies Q is equal to negation Q implies negation P. Now I am applying this one for this one. Now what happens? Negation E implies negation K, we will get the result. Now by using these two, okay, So that is C implies negation E, and negation E implies negation K. So now by using this, it is just like A implies B, and it is a B implies C, means we got the result as A implies C. So that the result is C implies, okay, so this negation E cancelled, C implies negation K as a final result. Okay, so now from these two statements, what is the result is C implies negation K is the result. C means, so if he is a corrupted, then he will not be kind. So that is the final result we got here. Okay, so if he is a corrupted person, then he will not be a kind. Okay, so not K means he will not be a kind. Now here from these statements we need to check out the statement which will follow that one. If he is a corrupted, so just see there, if a person is known to be corrupt, he is a kind. Okay, but he should not be kind. So if he are not here, then it will be correct, so that it is not the case. If a person is not known to be correct, okay, that means here negation C. Okay, that means here it can also be written as negation, that is K implies negation C, like that you can write. Okay, but this is not possible. Okay, so it is also not considered. And coming to D here, if a person is not kind, he is not known to be corrupt. Okay, so both the sides not are there, so that it is also not possible. If a person is kind, see here, if a person is kind, then he is not known to be corrupt. So K means if a person is kind, then he is not corrupt. Okay, so that C is the correct answer. So for this one, so like that we can do this one. So this is the question 4. And coming to this question 5, okay, let us see here. This is how we can get the answer for this. Very simple. Just which one of the following predicate formula is not logically valid? Okay, here he is given that which one is not logically valid. Note that W is a predicate formula without any free occurrence of X. Here we have P of X as one of the predicate function, and W is a predicate formula, and X is a variable. Okay, so that variable is actually with the W, that is not linked to that. Okay, so now here from this, now we need to find out which is not logically valid. Okay, that means actually this is the equivalent formulas like that we given. So it should be equivalent to this one. It should be equivalent to this one. It should be equivalent to this one. Like that we need to check out. Okay, let us see here. Here if you say this, for all x, P of x or W. So actually these are the direct formulas that we can apply are considered here. So this is for all x, P of x or W. So now this universal quantifier is applied for all x, P of x and W. So for W, for all x is not applied. Why? Because that x is a free occurrence. So for W it is not related, so that it is correct. Next, there exists x, P of x and W. So here also it is same. So there exists x, P of x and W. Okay, and coming to D, there exists x, P of x implies W. Okay, there exists x, P of x implies W. But whenever we have implies here, it is not the case. We'll see why we are not getting this. Now coming to the C, C is the correct answer. Why? Because let us we have a small steps for this. For all x, P of x implies W. This is a given here. So for all x, so it is just like P implies Q. We have a formula P implies Q, that is negation P or Q. We can write here. So that is a negation of P of x or W. I can write this like this. Now here what I will do there is, so I will apply this for all x to these two predicates. So that is for all x, negation of P of x, or for this particular W, we cannot apply this particular for all x. Why? Because it is free occurrence, so that W will come as it is. Okay, so now here if you say this, if you are moving this negation to this side, so now negation if you comes here, so this R for all becomes there exists x, P of x or W. That will be the rule. Actually this is the equivalent formula for this one. Okay, so that it is not a logic, it is not equally correct to this one. Similarly, okay, so it is not actually valid, so it is also valid, we can prove that. Okay, so like that, negation of there exists x, P of x or W. If that is the formula here, So then we can consider here. So like that we can check out the answer for this one. So this is for what we can say answer for fifth one. Next, these are all actually, as I already told, the formulas which are related to this one. Okay, so here, which one of the following well-formed formula in the predicate calculus is not valid? See here, this is also formulas. Just I will give the clue, and you can try it with on your own. Implies he given. Okay, so that means here we have p implies q, everyone we have implies formula. Okay, that is p implies q we have here. So here, and he need to check out whether it is a valid or not valid. Suppose it is not valid, it is not valid means, okay, what is the meaning of this is it is false. Okay, so it is false means, so when your p implies q is false, okay, if you check the truth table, if p is true and q is false, so then only we'll get false. Okay, in all other cases we'll get true. Now from these formulas you have to check out which one is a true and which one will be the false. So then we come to know that that becomes the answer for this one. Okay, that means, so the first three are true. That means they are equivalent formulas. Okay, they are logically from this. Let us from the p we can logically derive to q. Like that, the first three are possible, but whereas the fourth one is not possible here. Okay, so that is the thing with respect to this one. So actually, why? Because it is also true here. For all x, p of x or q of x implies for all x or for all q of x. Okay, so that it is not possible. It is possible. That's why it is not becomes false. So both are true only will get here. So that this is the correct answer for this one, sixth one. Similarly, the seventh one also the same. Okay, same principle or the same idea we have to apply here. So if you see what is the basic idea behind this, which we are going to apply here. So here he is asking to prove tautology. Okay, so now between these formulas you have to check out whether it is a tautology or not. Okay, tautology means we need to get true. Okay, now here if you observe here, we have two kinds of symbols are there. So one is a by implies and other one is a implies symbol. So if you see this by conditional, it will be true if both the p and q are true or false. False or false, then it will be true. So that means for this case, we have to check out these two cases. And for the rest of the cases, we have three possible. So as it is implies, we have three possible cases are there. That means true, 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 sorry, false, false, and false, true. For these three cases, you have to check out the validity of this B, C, and D. So if you check out that, C will not follow that. So that C is the answer for this. All are representing the same. Okay, so the actually these two are the formulas. We have implication formulas and by implication formulas, like that we have in the discussion. In the theory, just if you go once you will get regarding that idea regarding. But if you want to prove this or if you want to find out the answer for this, then we can go like this. And coming to this one, here also the same kind of question is this: which one of the following Boolean expression is not a tautology? Okay, so here he is given Boolean expression, no problem. Here we have and or by implies connective. So we have to check out not a tautology. That means tautology means will get true for all the cases. Not a tautology means will not get true. Okay, so that it may be false or true or false combination. So if you see this B is the answer. For this kind of questions, it is preferable to check out that is what we can say, that is truth tables. With the truth tables we can go here, but see here how we can do this. So it is not a tautology he given. Okay, so not a tautology means, see there all are implied symbols. Okay, that means implies means when it will be false, if true and false, then only will get false. That means every expression we need to get suppose if you consider this particular D, I will go with one. A implies D implies A. Okay, so now here if it is A, this is one expression, this is an, so let it be P, this is Q here. Okay, so true, false. Okay, then only will get false. Let us here, if I given true here, A as a true, and here A need to be given as a true. Okay, Suppose if you are getting implies, in the case of implies, if you are getting this a value as true, whatever the value of b, what happens to this one? So this becomes true only. So true implies true will get true, so that it is not possible. So let us see the answer what we have here. So a by implies c, okay, implies negation of b implies a and c. So this is the formula given. Now here, what is our requirement is, so this entire should be true and this one should be false. Okay, then it is not a valid expression. Now we can check out like this. So when it is a by implies, now when it will be true. Okay, if you go with this by implies means if both are true or both are false, then only it will be true. That means a value should be true, c value should be true, or otherwise a value should be false, c value should be false. Now see here, if you try to supply this a value as both true, that is what we can say true or true. Okay, a and c, if I given true and true, what happens to the final result? True and true means true will get here. That means negation b implies true will get here. Suppose if second value is true, automatically whatever the value of this one will get true here. Okay, and whereas if you consider the second case, if false and false if you are given there, so true, that is a and c becomes false now, and this negation b. Okay, so it should be what we need to get is to make it as a false. So here we need to get true. Okay, so now here if you need to get this true means your b value should be okay. So we need to get b value should be as true, so that so the c becomes the answer. So like that you can do this, or if you go in the brute force method way, directly you construct the truth table for every expression and you check out which is not following, which we are getting either true or false like that. So like that you can do. And coming to the ninth one here, this is actually formulas are there, shortcuts are there for this kind of questions. Okay, so the number of onto functions from the set x1 2 3 4 to the set abc. So how we are going to calculate this one? Actually we have the formula with respect to what we can say, how we are going to calculate number of possible functions for one to one, or what we can say onto functions, bijective functions like this. Suppose if you are asking for one to one, okay, so the formula may be like this. Okay, we have n c m into m factorial. So where n is the number of elements in the first set, m is the number of elements in the second set. So this is for one to one function. And coming to the number of onto functions that are possible. Okay, so here it is given by a small formula, little bit tricky, but no problem. So total number of functions minus, and then we have a formula like this, summation of, okay, n is equal, sorry, r equal to 1 to n minus 1 minus 1 to the power of n minus r multiplied by ncr into r to the power of m. So actually this is the formula for this one. Okay, so now here n value is 4 and m value is 3. So now based on these two values, so if you total number of functions, okay, so the total number of functions that we can calculate is it is again a small formula. Total number of functions is given by m to the power of n. Okay, so that is 3 to the power of 4 minus, okay, here if you apply this formula here, what we'll get is 3c1 and 2 to the power of 4 plus, so alternative will get a plus and minus. Similarly 3c2, like that we will get here, and here we'll get 1. So if you solve this one, we'll get 36 as the result. So only thing is just you try to remember this particular formulas. Number of one-to functions possible, number of onto functions possible. So if you are asking to either one to one or onto, okay, directly, so we need to subtract it from the total number of so this 3 to the power of 4 is total number of functions that are possible. From that we need to subtract this, so that we'll get the result for this one. So this is the way how we are going to do this. So next the another one, It is simple one. Let a group is given. Let G be a group of 35 35 elements. So then the largest possible size of the subgroup G other than G itself. Okay. So here we have G and G dash. Okay. So G dash is your subgroup. We will assume subgroup, and G is a group here. So there is a relation between the number of elements, or it is also called as the order of the graph. The number of elements is also called as order of the graph. Okay, in terms of manually, we can say like this. So order of your group, okay, not graph, sorry, order of group is equal to. So now what is the result for this one? We'll get it here is, so for if you see this order of subgroup, for the order for the subgroup, that is, it is equal to factors of, okay, whatever the number we given here, so that is going to be, let us 35. Okay, so now here if you see this one, for 35 the factors are like 1, 3, sorry, not 3, 5, 7 and 35. So now these are the factors for your number of elements, that is a group number of elements. So for subgroup, if you want to find out the number of elements that are possible, so we need to consider this particular factors for the number of elements in the group. Now here, the largest possible size of the subgroup. The size of the subgroup may be 1 or 5 or 7 or 35 subgroup of G other than G itself. That means other than G means 35 should not be considered. Okay, so if you are ignoring 35, and here we have only the maximum number possible, that is 7 only. So that 7 will be considered here. So that the answer is 7 for this. Okay, so this is next 10th one. Next 11th one. Here let us see here. The problem is given like this. Let R be the set of all binary relations on the set 1, 2, 3. Suppose a relation R is chosen from R at random. What is the probability that chosen relation is reflexive? So he is asking to round off the values to the 3 decimal places. Okay. So here we are going to do a small division. So it may be resulting to the more, after the decimal point, more number of digits may be there. So that is asking to round to the nearest integer. That is after the decimal point, 3 digits you need to get here. Now here a small formula is there. Okay, so actually this formula is he given the probability. He is asking to find out the probability, so that the probability is given by, okay, so number of total number of reflexive relations. Okay, number of reflexive relations that are possible by total number of relations. Okay, if he is asking only that is total number of reflexive relations, means we will go with this one. So as he is asking for probability from the total number of relations, only few of them are belonging to this reflexive relation, so that we will consider this particular fraction. And this is for this the formula is given. Number of reflexive relations are given by 2 to the power of n square minus n divided by number of relations are given by 2 to the power of n square. So this is the formula. And here what is the n value is? N value is 3. So that if you substitute that, so 2 power 3 square minus 3 divided by 2 power 3 square. So that is 2 power 9 minus 3, that is 6 by 2 power, here we will get 3 square, that is 9. So that is what we can say, 2 power 6, 2 power 3, 1 by 2 power 3, that is 1 by 8, that is equal to 0.125, like this. So this is the answer for this one. So like that we can do this. Similarly, next, just the thing is here we have to remember this formula. Okay, so and you have to check out whether he is asking for probability. Normally to get wrong, try to do this one. So next one, let G is a arbitrary group. Consider the following relations on the group. So first relation R1 is given by, for all A, comma A, B belongs to G, A is related to B in such a way that there exists G belongs to G such that A is equal to G inverse of BG. Okay, this is the relation given. Okay, next similarly R2 is given by A is equal to B inverse. So this is another relation given. So now he is asking to check out which of the two relations are belonging to equivalence relation, whether both are only one, like that. Okay, now equivalence relation means it should follow three properties, as we know already. So it should follow reflexive property, second one is symmetric property, and third one is transitive property. Okay, we know already about this. Reflexive means A should be related to A. Symmetric means if A is related to B, B should be related to A. Transitive means A is related to B, B is related to C, means A should be related to C. So this is the thing we have to hear. So now we will check whether these particular properties are followed or not. Okay, so it is just you can check out here very easily. Suppose here, first see the first one regarding that R1 relation. So here A is equal to G inverse of B into Z. Okay, so now if you are applying this relation, what we need to get, A should be related to A only, B should be related to B only. So like that we need to get the answer. Now here, if you substitute an identity element in the place of B, okay, so G inverse into Z into B. So G inverse Z will be G, okay. So that is one will get, and here we'll get here that is in the place of B. If you substitute that is identity element, okay, so we'll get E here. So this G inverse G is A only, okay. So now it is possible to get A into A. A is equal to A. So we can say that this one will follow reflexive property. Whereas coming to this one, so there is no way that A will get the answer as A. Why? Because A is equal to B inverse we have here. So reflexive property is not at all possible for the second relation. So that if any one of the properties fail, no need to check other. So that the R2 will not be a equivalence relation. Only R1 is the equivalence relation. So that we can say that R1 only is following the this particular property. So this 12th one. So next 13th one here, let us the question is like this. Let u equal to 1, 2, 3 up to n, let it be a universal set, and a is equal to x comma capital X such that x belongs to x and capital X is subset or equal to u. Now consider the following two statements on that order of, so that is a what we can say cardinality of A, number of elements in the set, given set. Now what is actually this meaning is, so universal set is given here, and a relation, it is actually a relation. Now what the relation will contain is, it will contain the elements in such a way that, okay, here we have a set X, okay, so this X is subset or equal to U. Let us here X is equal to, we'll assume 1, 2, 3 like this, and universal set is, it is 1 to up to n. Okay, now what is the ordered pair format is, let us x small x belongs to capital X, so that 1 comma, so again here we have the set X. Next similarly 2 comma, again we have the set X. So like that the relation will contain the ordered pairs. Now he is asking about what is the total number of elements that are possible in the relation. Okay, so in the relation, how many number of elements that are possible. So if you want to find out that one, okay, actually these are the direct formulas that we can consider here. So if you apply that particular, actually the formulas are both true. Okay, so we can use this one or this one to find out the total number of elements which will follow this particular relation. Actually, if you see the, it is the first one is a direct formula. Second one is just to get confused, to make confusion here. So this is NCK, means this is nothing but NCR. Actually, this NCR represents the total number of elements in the subset, in the set, with the K number of elements as a subset. Okay, so NCR represents the total number of elements in the in the set, with the subset size is K, or that particular, that is R. Okay, so that is given by this NCK, and why we multiply this K is, so to get the total number of ordered pairs in the relation, we multiplied this. Okay, so that if you with these two statements are true for this one. So this is the way how we are going to do this one. So this is one, and similarly this is also direct formula that we can apply here, which is going to be the problem on the set. And let us see one more simple one. Okay, so for this one, the formula that we are going to, the previous one, we are going to apply the formula for this. Next one, the cardinality of the power set of 0, 1 to 10 elements is given by. So actually, this is very simple and a direct formula we have here. What is the formula here is, so we know already the total number of elements in the subset is given by 2 to the power of n. Okay, so now in the set totally how many elements are there means, so in the, if you are doing fast way we will assume that it's 10, but it is not 10, 0 also there, so that it is 11, so that it is 2 to the power of 11. So 2 to the power of 11 is equal to 2048. So this is another question which we can easily answer this one. Similarly, we can check out about the properties. So here given a relation, and we can check out which property is followed for this one. Okay, so we can assume the values for the relation whatever is given, and based on that we can check out whether the properties are followed or not. Let us see here. The relation is defined on the set of positive integers. Okay, so that the set will contain 1, 2, 3, 4, 5, and so on, such that uh, if A and B are distinct and have a common divisor, okay, if you consider any two elements in such a way that they will have a common divisor other than one. So we need to consider the ordered pairs in such a way that, so they should not, they will have a common divisor. Okay, let us see here. One will have 1 comma 1, next 1 comma 2, 1 comma 3, like that we can consider with the combination 1. Coming to 2, 2 comma 3 not possible. Why? Because 2, 3 they don't have a common divisor. Next 2 comma 4 is possible, 2 comma 6 is possible. Similarly, 2 comma 8 is possible. Coming to 3, 3 comma 4, 3 comma 5, 3. So lower elements no need to consider. 3, 4, 3, 5, 3, 6 is possible. Okay. Next, similarly, 3, 9 is possible. So like that, just you identify the ordered pairs, okay, and see that which one of the following statement about R is true. He just asking that whether which property is followed here: reflexive, symmetric, transitive. So these three properties you have to check out here. So if you check out this ordered pairs with this one symmetric, R is symmetric but not reflexive and not transitive. Okay, so that is the case how we are going to solve this one. So similarly, the other problems are there. You may get directly regarding this one. Okay. So this is regarding today's session. Okay. Thank you for all of you.